We are team 165, and we are detecting brain cancer in MRIs via image recognition in neural nets. So our motivation is that brain cancer is one of the deadliest forms of cancer, with the average 5-year survival rate being 1 in 3. So early detection, as you can guess, is essential so that patients can get outcomes earlier and diagnosis earlier so they can get treatment earlier. And so our goal is to use a machine learning algorithm to assist clinicians with diagnosing. So our data source is 2 Kaggle brain tumor MRI datasets that we actually merged into one. So there are 7,000 MRIs that are labeled yes and no, and there were some that also were different categories, but we are just doing a binary classification. So we just put those into the yes or no category, and we assume these MRIs to be correct since they were performed by trained technicians. So our inputs and outputs, we input the raw 2D JPEG, which we pre-process. We normalize it. We put it into the same shape, and then we put that into our machine learning model, which then outputs a binary classification. We did look at doing contrast enhancement and noise reduction, but ultimately we did not go with those. So the outcomes for this, if the tumor detection is correct, that can lead to early diagnosis and treatment, which is good for the patient. If it's a false positive, this can lead to unnecessary tests, but hopefully won't be anything too serious. But if it's a false negative, this will lead to a misdiagnosis, which can be very bad for the patient. So our neural network is based on the EfficientNet B0, which has a unique STEM architecture, but we decided to go with our own. We built our own architecture, although it is based on this. And so we have these STEM layers, which consist of a convolutional layer, batch normalization, ReLU activation, and then max pooling. And we have 2 of those side by side. And then we go into the linear layers to help with the actual binary output. And this is our code. And as you can see, the images start as RBG values. And we did look at doing a grayscale as well. So how do we evaluate our neural net? We did 20 epochs with a 1e to the -4th learning rate using the ADAM optimization. We did look at other things, which we will show later on. In our matrix, we're using 3 matrix. For both training and validation, we're using accuracy, precision, and F1 score. And then we take this one with the best accuracy, and that is our model. So as you can see some of our graphs here, we have loss, accuracy, F1 score, which is a blend of precision and recall, and precision. So let's start with loss. You can see that the loss in general goes in the general trend that we want, which is down. At the end, it goes up, which is probably due to starting to overfit or something like that. So as you can see, that's where we start training, which is probably a good idea. And with the other matrix, you can see that in general, the blue one is the training and the orange one is validation. So in general, the blue line, both of them go up, but the blue line in general goes up a little smoother, which is good. And as you can see, they start dipping down, which is probably due to overfitting. And then the yellow line is a little jagged, which means that we could probably work on smoothing some things out with different rates or something like that, more pre-processing. But in general, it goes in the right direction. So our test results, we were able to get our model to 97.65% accuracy. And as you can see in the right here, this is what our model is being fed and predicting on. And you can see out of these 9 images, the middle one is actually wrong. It's supposed to be that there is a tumor, and it predicted that there's not a tumor. And so this is why we emphasize that this is supposed to be assisting clinicians and not replacing clinicians, because both clinicians and neural nets can be wrong, but together they will hopefully be better. So comparison to baseline, this actually was our baseline. We started with like 2 or 3 different models. We tried them out. We got this one working really, really well, as you can see. And we have been trying some things to help improve it in different things, but we have not been able to surpass that 97% threshold. So some things we have tried. We tried more convolutional layers, system layers. This actually led to a lower result, which is probably due to overfitting. We tried a higher learning rate, and this also had even worse precision accuracy. This is probably due to it keep passing the minima and not being able to float down to that minima. And as you can see in the graph there, this is with, I believe, the higher learning rate, which I can see is more jagged and going all over the place. We'd also tried a scheduler to help slow down the learning rate. That did not help us too much. And we also tried using EfficientNet B0 directly, doing transfer learning at our own layers. But again, we were not able to get it up to that 97.65% accuracy, probably due to the fact that EfficientNet B0 is for classifying a bunch of different images, almost like YOLO. So all of these, we got about 95% accuracy, so just under what we were getting with our neural net. So in conclusion, we were able to train a neural network architecture that was able to detect pretty fairly accurately whether or not there are tumor in brain MRI images. And of course, this can be further improved by doing different things like smoothing, maybe adding some different layers to it and drop out and stuff like that. But in general, we stress that this is supposed to be a tool to help clinicians make decisions and not replace them so that we can hopefully save lives. And these are our resources and references. And thank you very much.